DC circuits. In this circuit we have a voltmeter and an ammeter. We're trying to take some measurements in the circuit, and anytime you reach into a system to take a measurement, you're going to disturb the system slightly. So we design our instruments so that they disturb the system as little as possible. And in this case, we're dealing with an ideal voltmeter and an ideal ammeter. So they are not going to disturb the system at all. And that means that the voltmeter has infinite resistance and the ammeter has zero resistance. So I'm going to redraw this circuit, because basically what's happening, well, let's take a look at it here. If the voltmeter has infinite resistance, then it's basically an open circuit there. No current can get through the voltmeter, and the voltmeter is in series with R1, so no current can get through R1. So we can just take that out of our circuit. And if the ammeter has zero resistance, as the current is coming along this path here, when it gets to this point, it can split. Part of it can go through R3 and part of it can go through the ammeter. Well, as long as every path has some resistance, the current will split up and some current will take every path. Most of the current will take the path of least resistance, and some current will go on the path that has more resistance. It's kind of like getting to the line at the supermarket. You look at the lines, everyone wants to go to the quick check line where if you only have a couple of items. But once that line starts to get too long, you might decide it's quicker just to get into the other line behind the cart with the person that has 100 cans of cat food in there, and you're going to get behind them to pay, because it's quicker than waiting behind 20 people in the quick check line. So the electrons make the same decision. As long as every path has some resistance, the electrons will split up and some will take every path. But if one of those paths has zero resistance, which is the case here, then no electrons go any other path. All the electrons take the path of zero resistance. It's called a short. And so the ammeter is shorting out resistor 3. No current goes through resistor 3, so we can take it out of our circuit too. So all we really have here, let's just redraw this circuit. All we really have is R2 and our battery. And our voltmeter is reaching in and measuring across R2. Okay, so let me just quickly do the calculations. It's sort of trivial at this point. We only have one resistor and one battery, and we know V equals IR. So we know the voltage is 12 volts, and we know the resistance is 2 ohms, so we end up with a 6 amp current. So we know that our ammeter is reading 6 amps. That's what's flowing, that's the current that's flowing in this circuit. And our voltmeter is reading 12 volts. Because we've got 6 amps going through a 2 ohm resistor is 12 volts. But you can also see that, well, let me go back to the original circuit. And what I'm going to do, I like to do this a lot. I like to get out, my colored pencils or something. And let me start with yellow here. So let's call the bottom side of our battery, let's call that 0 volts. And I'm going to start here, and I'm going to draw 0 everywhere it's 0 volts. I'm going to put it in yellow. So conductors are what we call constant potential equipotential surfaces, right? So this is a perfect, these wires are perfect conductors, so they have to be the same potential everywhere. So once we call this 0 volts, we know it's 0 all through here. And that ammeter has no resistance. It does not affect the voltage at all. So that means on the top side of the ammeter, it's also 0 volts. So I'm going to mark 0 volts everywhere over here. So that's all 0 volts. Now you can see why we have no current going through R3, because it's the same voltage on both sides of that resistor. No current's going to go through it. Now let me get a different color. How about this color here? And I'm going to mark that. That's going to be, what's our battery, 12 volts? 12 volts. And I'm going to mark 12 volts in this blue color. And I'm just going to walk around the circuit, marking the lines that are 12 volts. I'm going to go right up to each resistor. Okay, so that's the easy part. Now I have to think about how I go through the resistors. So R2, it's pretty clear. It's 12 volts on one side of R2, 0 volts on the other side. I'm done with that one. But R1, I'm trying to figure out what's in between R1 and my voltmeter. And I know I've got no current going through R1. So if I have no current going through the resistor, I have 0 potential drop across that resistor. So both sides of the resistor have the same voltage. So if it's 12 volts on the left side of R1, it's going to be 12 volts on the right side of R1. So now you can see that the voltmeter, one side of the voltmeter is hooked up to 12 volts, the other side is hooked up to 0. It's going to be reading a 12 volt delta V. So this is kind of a neat technique. Walk through the circuit and mark on there what the top side of the battery is connected to, what the bottom side is connected to, and see if you can get through anything, voltmeters, ammeters, or resistors, capacitors, and maybe you can figure out what the voltages are using this technique.